Hi, welcome back to es346 Basic Thermodynamics. This is module 7.3. What is entropy? The section in the textbook is section 7.6. There's two learning outcomes for this module. At the end, you will understand the probabilistic nature of entropy, and you'll be able to describe processes that involve changes in entropy. So in the very first module, we saw this definition of what entropy was. It's del Q over T. And so if we wanted to know what the change in entropy is, we would just need to add up all the little bits of heat that we do each time normalized by temperature. So for example, I had some sort of box and it was initially at a temperature T1, and I was to put in 1 joule. And let's say T1 is, for example, 300 Kelvin. And I wanted to know what the change in entropy is after I went ahead and put in that 1 joule. I would just go ahead and put my 1 joule over 300 Kelvin. And I know that my entropy changed 0.00333 kilojoules per Kelvin. So that's how much the entropy changed. And now let's go ahead and put another joule in there. And let's say after the first joule, it went up to 301 Kelvin. And now I'm going to put one more joule in there. There's going to be a further increase in entropy of 1 joule, but now it's over 301 Kelvin. And so the entropy change is 0.00332, so slightly less. So what we realize is as I add another kilojoule of energy, the entropy is going up, but not as much. And there's a way to go ahead and find out what the change in entropy is for a process. It's sort of tedious to do. There's another way to look at entropy, and this comes to us from statistical mechanics, which is this equation due to Boltzmann, where the entropy, this is the total entropy now, is equal to K times the natural log of W. Now, K is the Boltzmann's constant. And it has a particular value as being a constant, and it is equal to 1.38 times 10 to the minus 23, and that is joules per Kelvin. Right? There would be a corresponding one in English units. So that's the value of K. And W is the number of different configurations something could take and have the same energy. Right? So what does that mean? Well, let's just take a real simple system here. I'm going to go ahead and take a crystal that has 4 molecules in it, and I'm going to go ahead and color 2 of them this way and 2 of them as white. And if I was to look at the different ways I could go ahead and put this crystal together, I'd realize I could put it together that way. And let's go ahead and restrict it to 2 dimensions here as well. I could go ahead and put them on the opposite side like that, or I could put them this way. And that's kind of the number of configurations possible for this crystal. And so in that case, W would be equal to 4. So if I want to know what the total entropy is, I'm going to go ahead and do it's going to be K times the ln of W. That's Stefan Boltzmann constant of 1.38 times 10 to the minus 23 joules per Kelvin times the natural log of 4, and that comes out to be 1.91 times 10 to the minus 23 joules per Kelvin. So there's another way to go ahead and determine what the entropy is. And what I realize is the more possible ways I can put this together, the larger the value of S. Right? Now this isn't particularly useful for us, as we'll see in classical thermodynamics, but this idea of number of configurations is a helpful thing to remember. So let's go to something more in the continuum, where now I have, say, a bunch of gas molecules contained in a tank. So here I show all my molecules bouncing around. And what we want to look at is what is the effect of pressure on entropy. So if you were to just glance at this and take a picture of it, and there's where all of my molecules are, but then I was to go ahead and look a second later, they may look in this configuration. Go back. There it is at one point. There it is second later, right? Second before, second later. So we realize it all kind of moved around. And so this right here is yet one more configuration that I can have. So you want to think of it, this would be one value of W. This would be W equal to 1. Right? Now W is equal to 2. And I would need to come up with all the different configurations that I can take. And then to find out what the total entropy is, it would end up being K ln of W. Now, W, you could realize, would be pretty large. It depends on how much space I have in here and how many molecules I have. Okay. Well, now imagine I take this tank keep the same number of molecules in it. I'm going to go ahead and keep the temperature constant, so it's a similar energy system. And I'm going to go ahead and compress it down, right? But temperature is going to be constant. So after I did the compression, I removed some heat to keep the temperature constant. So therefore, U is equal to a constant. So the energy state of these two systems is the same. But what I realize now is I've got a smaller system. There's less places that the molecules can go. So there's a lot. The value of W here is going to be much less than it was in the previous case, which means that the value of S in this case is going to be lower. So what we realize is that generally, if the pressure increases, the entropy is going to decrease because I'm confining the molecules to a smaller space, and the value of W in each case is going to be smaller as the pressure goes up. Let's look at the effect of temperature now. And so now I've got my box of molecules here, and so they're at some temperature T1, and say that that's 25 degrees Celsius. And then I go ahead and heat it up to maybe 200 degrees Celsius. What would be different if it was still in the box, the same number of molecules? Well, what I would find is that these molecules are going to be going with a much larger velocity. And in fact, what I show on the right-hand side here is a Boltzmann's distribution for gas molecules as a function of temperature. Let me explain what this is. Let's look at the cyan curve here. This is in the velocity in meters per second at 100 Kelvin, and this is the number of particles. And so it tells me there's going to be this many particles that have that velocity, this many particles with that one in here. And I realized it's sort of a narrow band, so there's not actually a lot of different configurations that it could take of different distributions of the arrow. So for example, large value of the velocity would be really fast. This one over here means that it's barely moving at all. Now as I go ahead and heat it up, let's look at the 1000 degrees in the red curve, I've got a much, much larger distribution. I've got molecules that could be going really fast and some really slow, or maybe I've just got some in the middle. There's more configurations that I can have, more distributions of different temperatures, mixtures that I can have. What that tells me is that as the temperature increases, the entropy increases, because again, W is going to be larger. There's more possible configurations of equal energy that I can. Just going to go through another thought problem here. I've got a thermos, and this is going to be a perfect thermos. It means that it's completely insulated. So I know Q is going to be equal to 0 for this thermos. And let's say initially T1 is 25 degrees Celsius. And I've got some fluid in here. Now what I'm going to do is I'm going to start shaking this around and shake it and shake it and shake it. And then after a while, I'm going to measure the temperature, and I find out that T2 is equal to 27 degrees Celsius. And my question is, did I change the entropy? Because I had no Q. And recall, delta S is equal to the integral of del Q over T. But I just said Q was equal to 0. So how can I have a change in entropy? Well, remember, this is a way to get it. If I went ahead and added up del Q over T from 25 to 27, if I added heat to the thermos, I could calculate what delta S is. But I can go ahead and still heat it up by friction, get it to 27 even though there's no heat transfer. It's just that then it's an irreversible process. So remember our TS diagrams where we would have a reversible process here. That's the one where I'm adding up del Q, and then here's the shaking of the thermos where Q is equal to 0, but it's irreversible. And so there's still a change in entropy, and it's the same if I'd followed the reversible path, that I can follow the irreversible path. And it turns out there's almost an infinite number of irreversible paths to arrive at this point, yet there's only one reversible path, which is this heat transfer normalized by temperature. Let's do one more thought problem here. It's kind of a mechanical problem. And what I have here is a gearbox, and so I go ahead and put work in there into that gear, and it turns these around, and I go ahead and get some work out. And so let's go ahead and imagine this gearbox is at a temperature of 30 degrees Celsius. And if I was to go ahead and start cranking on this gear here, and let's say I go ahead and crank with a power of 50 watts, that's what's going in, and then due to friction within the gears aren't perfect, I find out I only get 48 watts out. So that's the work going out. This is the work going in. Well, 50 watts going out. Due to friction, I'm only getting 48 watts out of this gear here, then clearly there must be another 2 watts, we know from the first law, somewhere that's coming in due to the friction in the grinding of the gear. So if I want to know how much entropy I'm generating, how much entropy am I generating? Well, what I've got is I've got this 2 watts here being left as heat, so I would have 2 watts normalized by the temperature, and I need to do this as, this will be 30 plus 273, and that'll tell me how much entropy I'm generating, which is 0.0066 watts per Kelvin. Right? So there's the entropy being generated due to the grinding of the gears and due to the friction. Now, let's go ahead and, okay, here's our gearbox. We said it was at 30 degrees, and clearly if we're dumping a little bit of heat, 2 watts, if we want to keep this at 30 degrees, that 2 watts has to continue to leave the system. Now, if it's going to leave the system, it has to be into something colder than 30. Let's say it's going into an environment that is 25. There's going to be entropy generation as the energy leaves the 30-degree gearbox and enters the 25 degrees. We can find out what that amount is, and so we'll just add up minus 2 watts that leaves the high temperature, so that's 30 degrees or 303 Kelvin. And then the 2 watts is entering this at 298 Kelvin or 25 degrees Celsius. And that comes out to be 0.11, this is milliwatts Kelvin. So there's the entropy being generated as the 2 watts crosses the boundary of the gearbox. And now if I want to know how much entropy is being generated in the entire universe, well, first I've got this 6.6 milliwatts per Kelvin due to friction, and then I need to add my 0.11 milliwatt Kelvin due to heat transfer, and that's the total entropy increase, which is 6.71 milliwatts per Kelvin. It's being generated in the universe. And again, just the units here, milliwatts, you could also think of this as millijoule per Kelvin second. Right? So that's the rate that entropy is being generated in the universe.